Hi, is everyone enjoying the conference? Great. Ready to hear a bit more about WebAssembly? Anyone interested in WebAssembly? Well, let's see. I unfortunately don't have a clicker, so it's a USB-C laptop. I'm actually on a Chromebook, so this is all web-based. So, as she said, my name is Kenneth. I'm Danish. I work at a company called Intel. You mostly know us from doing chipsets, but like hardware does nothing on its own. It needs software to enable it. So I am working in the web platform team on just improving the web and making the web work well for you and for Intel. If you want to follow me on Twitter, I'm going to tweet all the slides later, and you can follow me at Kenneth Road. I work on Chrome, and I work on standards as well. I've been a WebKit reviewer. I'm a Chrome owner as well. I worked on browsers since around 2006. Then I've gotten more into, actually I thought as a browser engineer, you need to understand how it is that people are actually writing for your platform. It's not enough just sitting and coding C++. You need to write those web apps yourself. You need to understand how people look at the platform. So I got involved with JavaScript and standards as well. So I am working in the W3C. I'm actually an elected member to what is called the Technical Architect Group at the W3C, where we're overlooking all the newest web standards. So today I'm going to take you on a journey to show you how cool the web platform has become. But first, what is this WebAssembly WASM thing? Well, let's have a look. The web is pretty awesome. Even my baby girl thinks that. But sometimes you need a bit more power. Or you have existing code bases written in native. Moving to the web might not be a piece of cake. But the web platform is about to change because we're getting a new feature called WebAssembly. So WebAssembly is going to enable a whole new class of web applications that are more capable and powerful than ever. We've already established that the web is a great platform because that's why we're here at JSCamp. It's safe. You're not afraid to go to different websites. People go on average, I think, around to more than 100, 200 websites per month. No one worries about that. There's also very low friction. You just type in a URL, and there you are. But while the web is all this great, so great, it also has a certain set of limitations. You don't see high-end games on the web. You don't see like CAD applications, professional video editors, and the like. Basically, you don't see applications that require a lot of calculations with low latency. Things that are CPU-bound, or what some people call close to the metal. Sometimes you can delegate some of these operations to the cloud, but of course, you have to pay to run it on the cloud, and you also introduce a certain set of latency because everything is going over the network. But with WebAssembly, things are changing. WebAssembly is a new capability for the web. It's a compile target for the languages usually used in native applications. It's a fast, portable, and secure. Formally, this is from the standard. It says WASM is a new portable, size and load time efficient format suitable for compilation to the web. So it's kind of like an efficient, low-level bytecode, but written for web applications. It's small, it's fast to load, and really efficient to execute. So you might wonder, is this a replacement for JavaScript? And you just heard that that is actually not the case. So let's try to get rid of some of the common misconceptions about WebAssembly. First of all, WebAssembly is not in itself a programming language. It is possible to write something manually, but that is not the intention. Nor is it intended to replace JavaScript. It's just a target for other existing languages such as Rust, C, and C++ that you can complement JavaScript with. WebAssembly also lives in a sandbox. So there's these people that believe that, now I have native access to everything. So suddenly I have access to file systems, USB devices, and all of this. No, you don't. So even if you take like a native application, you want to port it to WebAssembly, well, if it's using a certain audio library or OpenGL, it doesn't naturally just like work on the web because that doesn't exist on the web. You'll have to map it like to a canvas or to WebGL or something similar. So it lives in the same sandbox as everything else on the web, and there are no special hooks. However, in the long term, there's a certain features that we might not, and it might not so easy to add to JavaScript itself, but we can add to WebAssembly. Especially because if you have a large JavaScript application and you do like computations and you find there's a bottleneck, it might be possible to re-implement that part of the code in WebAssembly. And then take advantage of things that it's really difficult to add to JavaScript, like threads and single instruction multiple data. Single instruction multiple data is a very common thing in newer CPUs. It allows you, instead of like adding 2 numbers in one instruction, you might be able to add 4 numbers or 8 numbers, depending on what the CPU supports. So things like this is very common in games and computations. And this is something we don't have access to on the web today. But we're now adding that to WebAssembly. WebAssembly is really perfect for a lot of the use cases where the web currently doesn't shine. So for instance, game engines. Game engines are very self-contained. They don't use DOM elements and whatnot. So this is really great because they just need a place to draw, something like WebGL, and then they need their own logic. So they're really self-contained, and they work really well with WebAssembly. But like as I said before, if you have a game and it's using an auto library, you need somehow to do the mapping between what is on the web platform and what you're using in the native app. Luckily, there exist tools like Mscripten that does a lot of that for you. Other apps we don't see that will be really perfect for WebAssembly, something like CAD or video and photo editors. Here's an example of Google Earth actually running in Firefox. Google already have a version using their own proprietary system called Native Client or Pinnacle or Portable Native Client, but they're making a new version using WebAssembly. And that will work cross-platform, thus not only in Chrome, but also in Firefox and Edge. Here's an example that Google was showcasing at Google I/O. This is Autodesk. Autodesk have this enormous code base they've written over 35 years. And now they can just do a bit of work and compile that into a view, an editor view on the web. And then they can just redo all the toolbars and whatever using regular web technology, getting the best of both worlds, and getting something that's truly portable across OSs. So this is really important part of WebAssembly. There is so much code out there, so many libraries that are optimized for decoding or for crypto and whatnot. And it's really great that we don't need to reinvent all of this, that suddenly we just have access to this huge catalog of software. So one example that I came up when people asked me, what could you do with this? And this is one of the things we're looking at today is that, well, if the browser doesn't support a specific like image format or video format, would it be possible to use something like WebAssembly to make it support it out of the box without you having to do anything special? So let's use that as an example. So this was my journey to try to make this work. So first of all, what is WebP? WebP is a format, it's a really efficient image format. It's something like JPEG, but it's much more modern. It means there's higher quality, and the files are much smaller. Thus, it improves your loading time. But it's only supported in Chrome. So a lot of people are like, yeah, I cannot really use WebP because I need to support other platforms, unless they're doing some checking on the server. Currently, I think like I saw like a video on YouTube last week, and Microsoft actually announced that they're working on adding WebP to Edge. But we don't have WebP in Edge today, and we don't have it in Firefox. So can we make that work? So what I did is that I found the library. So WebP is called libwebp. It's a C library. So I can write my own small C application that can decode WebP images. I actually was surprised to find out that someone had already submitted code to the library that allowed it to be compiled to WebAssembly. So I thought that's pretty cool. It uses Canvas, this is the way they did it, because the library used something called SDL, which was being mapped to a Canvas tag. So it was pretty cool. I made this work in the browser pretty quickly. I'm using this tool chain called Mscripten. This is originally developed by Mozilla for their prior approach to WebAssembly called Asm.js. So Mscripten is really cool because it doesn't just compile your code to WebAssembly, but it also creates the mapping. So if you're using OpenGL, that will map to WebGL. If you're using a common, like SGL, that will also map to WebGL. Common audio libraries will map to web audio. Because the way it works with WebAssembly is that when you import a WebAssembly module, it comes with export, just like in JavaScript, function you can call. But it also takes imports, JavaScript calls that it needs to call to be able to do all of these things, to do this mapping. So this is just a simple example of how I could use like mscripting. You don't need to really understand this. You could find this in documentation. So I'm just like compiling a CNC code. And sometimes you need to export some function. You need to change your code a little bit so it doesn't optimize away the functions you want to call. But let's just have a quick look at the first JavaScript code that I wrote. So this is basically what I did. I did a set of input buttons, and I'm using JavaScript to load it. This is really not transparent. It's not just like doing an image tag with a WebP image. The first thing I'm doing when I'm loading, first of all, I await a promise. This is called a wait promise. This is just so that I'm sure that I have access to the module, because it needs to be imported first. When it's available, I actually go and fetch the original file. The data of this file, the buffer, I give to this function that I've written in WebAssembly called decode WebP buffer to canvas. And then I generate a data URL from the canvas, a use URL in base 64 format, just to make this work. But it actually works pretty well, as you saw before. That was the first thing I did, and I thought it was like, wow, this is really amazing, you can do these things. But I was wondering, maybe we could use something like a service worker. So what is a service worker? Service worker 101. Service worker is it's a worker, so it's like a thread in JavaScript or in the web platform, but it sits between the servers and the client. So it's kind of like a proxy server. But so for instance, if you're offline, it's possible for you to get like a file from a cache or generate some code or maybe some HTML and send that back instead. So this is so cool. It can intercept fetches. So I can generate something in JavaScript and return instead, or maybe I could just call it WebAssembly code. So I set out to try doing this. So I have a sneak preview. Now I'll see if I can get this on the other screen. So though this is a Chromebook, I actually also running Firefox on my Chromebook, because that's possible today. So these are actually WebP images. And if you look at the source code, just look at this part of it. You see these are just like regular image tags using WebP. And if you don't trust me, we can try reloading it. Let's hope the internet connection is good. Yep, there you go. What you see on the other side is it's actually fetching WebP images. You should probably see the headers. Let me see if I can find it. But these are WebP images. And then it returns instead. This is the end result, what I'm getting to. They turn these into BMP images, which is basically a raw data format with a few headers. And Firefox can render that without any problem. So this is really, really transparent. This is the end result. Let's get back to the slide set. This is the same thing running in Chrome, but Chrome already supports it out of the box. So my initial approach was, let's run WebAssembly, the WebAssembly module, in a service worker. Every time it tries to fetch a file and it's a WebP file, then I intercept that, and somehow I return the data. I use this WebAssembly module and return that back to the element. And that has to be as a blob. Initially, I was using it as an image.png block. And instead of like these huge data URLs. Some of the challenges I had was that, well, in order to generate this image BMP blob, and it uses Canvas by default, I kind of need to use Canvas, and I need to do that from Canvas. But there is no Canvas support in workers, and thus not in service workers. But there is this new API coming to the web platform called off-screen canvas. And that was available in both Firefox and Chrome behind the flag. Unfortunately, the API between the two implementations is different, and it was only reliable in Chrome. It crashed a lot in Firefox. But this, if you look at the support for this feature, it's pretty bad. So this is not really something you can use in production. But anyway, it's cool. Let's try. Let's see if we can do this. So this is my first attempt, and you saw, oh, it's actually working pretty well in Chrome. Pretty nice. It even works in Firefox. This is actually Firefox running on Android on Chrome OS. That also works. So let's have a look at the code and try to see if I can understand and show you how this actually works. So this is my approach. My approach was to create my own library. I didn't want to use using libwebp, so it's a C library, very small. It will decode to RGBA, so red, green, blue with alpha. Then this WebAssembly will give me this back. The way it works with WebAssembly is if you import a WebAssembly module, it also generates a buffer, like a heap, where it stores all its data. This is where a C++, like a C++ application or C application, can allocate and deallocate memory. So when I'm using the function, it's going to write into that buffer the result. Then I'm going to take this result, and I'm going to copy it into a JavaScript object. So it's going to be controlled by the garbage collector. And then I'll free the one that's living in WebAssembly land. From this, I'm going to generate something called image data, because this allows me to paint it to a canvas. And then I'm going to use an API from this off-screen canvas to actually get an image blob, like an image PNG blob. And then that was actually what I was doing. Very complicated, but I hope you can follow this. So this is the first code. This is my very small C library. So I know that a lot of you might not know C, but let's go over it very quickly. First of all, I need to import some things like mscripten, because I'm using this mscripten. Then I generate two functions. We'll look at the functions later. One called getInfo. I needed that because I need to know the size of the image. So I need to know the width and the height. Then I know the amount of pixels. So as this is a C application, I need to allocate memory. You do that in C using something called malloc. It stands for memory allocation. And we're back. So it stands for memory allocation. Basically, what is easy for me to deal with in JavaScript is an array, because it's a sequence of data. So I'm just creating an array of size 3. So this is a 32-bit array of size 3. And I use that the first value I store is whether this actually made sense, whether I was actually trying to decode a WebP image. So it's like a success or failure. And then I decode like the width and the height. The other function I did was the actual decode function that takes the data and the size, and it will actually give me a different buffer, or an address where it has stored the resulting buffer. In order to get all of this compiled, I really, really hate building tools, but I looked up and I found this called CMake, and I made it work. I just added that to my package JSON file, so I could just run npm run build, and it just compiled for me. So this is actually how the file looked. I don't even remember how I did it, but it's actually not that complicated. So instead of using automake and all of these other systems, I really encourage people to try looking at CMake. This is my decoder. So I wrote like a small object called WebP decoder, which is kind of like the object I'm using to decode these images. So the first you need to do using mscripten. Mscripten has a certain set. Like I said, it's not just WebAssembly. You also need to import some JavaScript, hooking up like OpenGL with WebGL and all of that, some boilerplate code. Then you need to wrap these C functions to something you can call from JavaScript. So this is just using the mscripten API. From this, I'm adding 3 functions or 3 methods to my object. Info, that will give me the sizes. Decode, that will decode it. And a special function that allows me to decode directly to a blob using a canvas. So let's look at each of these functions and how I did that. So here we have the same function we saw before, getInfo. So as I said, it gives me a pointer back to an array of 3 values. As these are 32 bits, it means that they are 4 bytes long. 32 divided by 8. That is why I'm using the offset later down when I'm getting width and height by pointer, the address, plus 4, and later plus 8. When I have these values, now they're in JavaScript land, in garbage collection land, I can free the original C code. So I'm freeing the object that was allocated in C. Decode is, in order to understand decode, there's a few things we need to remember. First of all, the library will store all the data on the WASM heap. This heap is accessible, so it's like a buffer. It's accessible from JavaScript. From there, I need to copy it so I can free the original and get it over in garbage collection land. So that is what I'm doing here. I call decode, the second line. I get an address back, or what is called a pointer. Then I create because it's just a pointer, it's just an address. I want to get a real array. Then I create like an array view. So this is not copying the data. It just makes me able to see the data, understand it as an array. So that's the first thing I do. That is when I generate a uint, the unsigned integer 8 array. And I do that using a special version, a special function from mscripting that allows me to get access to this heap. This is the module.heap unsigned integer 8.buffer. Then from there, I create a copy. This is the const result equal new uint 8 clamped array. Then I free the original, everything in C land, and return the actual JavaScript data. Decode to blob, I'm reusing this function. Furthermore, I'm generating this image data, from the buffer. Then I paint that to a canvas, and I use some of these special functions to get a blob out. So this looks like this. First of all, I get the width and height, so I know the size of the buffer. Then I decode the data, and I generate this image data object. So that takes like actually the data plus the width and the height, exactly what I had. Then I actually paint that to my off-screen buffer. And then I use this, and now you see there's a difference between the APIs in Firefox and Chrome. There's like 2 different ways of actually converting this to a blob. So I'm doing this, and it actually works. So the only big problem with this approach, though it works really well, is that off-screen canvas is not shipping anywhere yet. And there's, of course, also a lot of overhead that I need to generate this image, and then I need to paint it to a canvas, and then I need to generate a blob from a canvas. So I'm doing a lot of implicit copies of the data. So I was wondering, maybe there is a better approach. We can do better. So I wrote this article, I put it up on Medium, and one of the guys at Google that works in standard, he wrote me like, why don't you use BMP? Every browser out there supports BMP. BMP is a very simple format. It's basically raw data, like no compression. At least it's possible to do without any compression at all. And there's some certain set of headers. So you can just like generate that yourself. So then you generate your own image BMP blob and just like paint that. You don't need any canvas, no copies, much better. So I looked up, I remember that I used BMP back in university time when I was doing my first race tracer and I had to get an image out. So like, yeah, maybe they have some information about that. So I looked it up on Wikipedia. This might seem a bit overwhelming, but it's just a header. It's just you go through every one of these steps. What is this image, like image width, image height? This is the amount of code it took for me. So this is my small BMP encoder. Using this BMP encoder, I added this new function new method called decode to BMP. So when it has the image data, it just like calls this BMP, the image decoder, encode. And then it will get an image BMP blob back. This is how I'm actually doing it in the service worker. So in the service worker, when you get a fetch, the first thing you're checking is this actually a get method? And is it actually a WebP image? I should probably check the MIME type, but here I'm just like checking whether it ends on .webp. This is just an approach just to test anyway. Then when I actually get this data, I actually go out and get the original source, the actual WebP file. I get the data of it. This is called the .array buffer. Then I access my WebAssembly module. A service worker gets killed when you don't use it for a while, so you always have to get this WebAssembly again if it got killed. Then from that, I actually just generate my WebP decoder on top of the data, and I decode to BMP, and I return that as a response, as a blob response. And it just works. It's really, really amazing to see that you can do this today with something like WebAssembly. So, success. So my final approach was to generate a library in C using libwebp. I decoded to like RGBA, made sure that I copied all that data from the WebAssembly world to the JavaScript world, cleaned up memory. Then I took that and turned that into a BMP blob and just returned that to the main thread from the service worker. And from an endpoint user, you just install this service worker. You don't need to use any JavaScript. Suddenly, you can just use WebP images in browsers that don't support it natively. So I think it really shows that WebAssembly is really cool, and it allows you to integrate with existing APIs and libraries that already exist out there, like WebP, highly optimized native library for decoding WebP images. It also shows that mscripting is super useful, because if you had to do all this mapping yourself, I think there's a lot of people that wouldn't even play around with WebAssembly, because then the only thing you could do was simple things like adding a few numbers, but when you had to do something real, it would just become too complicated. It also shows that WebAssembly is usable today, and it can be integrated and called from a service worker. So go play with service worker, and thank you for listening.